You sit where you always sit, your body in this familiar space, the light from a window or a lamp touching your skin. Outside, night falls or day rises, and the motions of the world feel continuous, predictable. You assume time moves steadily forward, that the events you perceive are part of a coherent flow. You assume the universe, at least on large scales, behaves like the simple models you learned in school. Galaxies receding at predictable rates, stars forming and dying, space stretching uniformly. But the James Webb Space Telescope has begun to show you a different pattern. Light from galaxies formed only a few 100 million years after the Big Bang reaches you now, not as faint echoes of a distant past, but as fully structured, surprisingly mature systems. Structures exist that standard cosmology suggests should not yet have formed. Measurements align internally, yet they collectively resist your assumptions about temporal and spatial scale. The universe appears older, its behavior, than the time you assign to it, and younger in the raw age of its light than your models predict. You confront a paradox embedded in the data itself. The further you look, the more you measure a universe whose apparent age and complexity are inconsistent with your expectations. These are not anomalies of interpretation. They are consistent, repeatable observations, cataloged with precision. What does it mean when the cosmos reveals maturity where you expected infancy, structure where only uniformity should exist, and time flowing in a manner that undermines the very scales you take for granted? This video will explore the true scale of cosmic time as revealed by the James Webb Space Telescope and the unsettling implications that arise when your assumptions about the age, formation, and flow of the universe collide with what we now measure. The universe in your room. You assume your immediate surroundings are stable, governed by ordinary physics. Gravity holds, light travels in straight lines, and causality seems unquestioned. Yet the same rules applied on cosmic scales begin to distort, revealing patterns and motions that defy the intuitions you carry from your room to the cosmos. You are grounded in everyday scale, where distances are measured in meters, seconds tick uniformly, and objects behave predictably. Your perception of continuity and coherence is reinforced by every ordinary interaction. A pen falls, a lamp illuminates, a sound propagates, and all obeys a temporal order that seems absolute. Step beyond these familiar boundaries. Consider a galaxy, billions of light years away, whose light reaches you after traveling through expanding space. What you see is not its present, but its ancient state, frozen in a period barely after the universe itself emerged. The rules you rely on locally, smooth causality, predictable intervals, gradual accumulation, begin to fracture. Gravity, the force that seems so familiar when holding objects in your hand, has acted over such immense distances and times that its effects produce configurations unimaginable in ordinary experience. Spirals rotate, stars cluster, black holes grow, all in ways that suggest underlying regularity. Yet the timing and scale of their emergence cannot be traced by simple intuition. Light itself becomes deceptive. Photons leaving a distant galaxy are stretched, shifted by the expansion of space. Redshift is not merely a change in color. It encodes distance, time, and motion simultaneously. The straight path you assume for light in your room no longer applies. Light is bent, delayed, sometimes amplified or distorted by massive intervening structures. You observe multiple images of the same object, arcs and rings created by gravitational lensing. What you perceive as a single point is a composite of overlapping histories. The universe behaves as though it has memory. And yet that memory is not linear. Even space itself ceases to feel constant. Distances you imagine as intuitive, one galaxy twice as far as another, are complicated by expansion rates, by local density, by curvature. The voids and filaments of the cosmic web are mapped not by sight, but by inference. Yet their geometry produces measurable effects on the propagation of light, the motion of galaxies, and the timing of cosmic events. The room you occupy in the universe, while seemingly unchanging, is embedded in a larger space whose scale, shape, and evolution are dynamic. Expansion is uniform only in principle. Locally, it warps, accelerates, decelerates. The rules you trust are statistical, averaged over scales far beyond your perception. Time, too, behaves differently. Seconds measured on your wrist are uniform, yet the processes shaping distant galaxies occur on scales of millions or billions of years. The progression of events is uneven. Stars ignite and die in rapid succession. Supermassive black holes form earlier than expected, and galactic structures evolve with a speed that contradicts naive expectations of linear growth. Temporal order is not violated, but the rate of change is incomprehensible from your point of view. You confront a universe in which duration is relative, where the apparent age of structures cannot be deduced from simple observation. Your room, by contrast, remains predictable, yet the same laws, gravity, thermodynamics, electromagnetism, scale up to govern the cosmos in ways that defy intuition. Measurement anchors you. Spectral lines, redshifts, luminosities, and masses all provide precise data. Observation confirms reality. But the more you measure, the more the contrast grows between the immediate stability around you and the vast, unsteady, counterintuitive cosmos beyond. You realize that your ordinary perception of space and time is only a local approximation, an emergent simplification. Beyond your immediate sphere, the universe obeys the same fundamental laws, yet manifests them in ways that challenge your assumptions, in patterns that are precise yet unfathomable, familiar yet alien. Your room is a reference frame, a small, bounded domain. Beyond it, reality unfolds on scales that render intuition unreliable. The cosmos is ordered, measurable, consistent, but its order is subtle, distributed, and often at odds with what seems reasonable. Every observation you make, every photon received, every galaxy mapped, reinforces this dissonance. The universe in your room is simple. The universe outside it is not. And yet both are one. Both are equally governed by the same rules. You are confronted with the quiet, unavoidable fact that scale changes everything. Measuring light across billions of years. Light is the most basic measure of distance and time in astronomy. You trust that its journey encodes a simple story. Further away means older. But when James Webb observes galaxies whose light has traveled nearly 13 billion years, you encounter evidence that structure, formation, and evolution do not scale linearly with time. You imagine light as a messenger, carrying information across space with a regularity you can rely on. Each photon leaves a distant star, travels through the vacuum of space, and arrives at your instruments as a precise record of past events. It is a natural clock, a bridge between epochs. Yet, what these photons convey is often inconsistent with your expectation of gradual, incremental development. The first complication arises in the sheer maturity of these early galaxies. You expect that in the first few 100 million years after the Big Bang, matter should be dispersed, chaotic, and only beginning to coalesce. Yet light captured by James Webb reveals galaxies that are surprisingly massive, with well-formed cores, coherent spirals, and active star clusters. The photons arrive with spectral signatures that imply chemical enrichment, indicating multiple generations of stars already lived and died. You confront the dissonance. The story carried by light suggests a universe that has progressed further than time alone should allow. Redshift, the the stretching of light, waves as space itself expands, is your primary tool for relating distance to time. It is precise and reliable, grounded in general relativity and repeated observation. Yet even when redshift is carefully measured, the timeline inferred from the data clashes with theoretical models. Galaxies that should appear small, primitive, and diffuse instead present organization and energy output inconsistent with their chronological placement. The farther you look, the more light contradicts the assumption that cosmic evolution is slow, steady, and uniform. Light also illuminates inconsistencies in stellar populations. Photons in the infrared spectrum reveal stars formed earlier and in greater numbers than standard models predict. Clusters emit radiation that implies a complex history of formation compressed into periods that, according to your assumptions, should be insufficient for such development. You perceive the universe as though watching a movie played at irregular speed. Some scenes unfold slowly. Others appear to have already completed entire sequences in the time allotted for a single frame. Measurement confirms this. The irregularities are precise, repeatable, and independent of observational error. Moreover, light exposes the paradox of scale. Individual galaxies carry signals that imply rapid internal evolution, while the large-scale structure of the universe, its filaments, voids, and clusters, follows patterns that emerge over billions of years. You measure both simultaneously. The same photons trace microcosmic processes within galaxies and macrocosmic flows across vast distances. Your intuition, trained to separate local and global phenomena, fails. The universe appears to accelerate and decelerate at different scales, yet this is not speculation. It is the unavoidable conclusion drawn from light that reaches your instruments, unaltered across unimaginable distances. Intervening matter further complicates the narrative. Dust, gas, and gravitational fields alter the path and energy of photons, creating lensing, absorption, and redirection. Each photon you measure is not a simple line from source to observer, but a record of interactions, deflections, and delays. The story carried by light is not straightforward chronology. It is a convolution of causality, motion, and interaction, requiring careful deconstruction to extract the temporal sequence you seek. Even then, the sequence often appears compressed, accelerated, or nonlinear. Ultimately, measuring light across billions of years forces you to confront a disquieting implication. Time, as you perceive it locally, may not map directly onto the cosmos. Your chronological intuitions, linear, cumulative, and uniform, do not correspond perfectly to the events revealed in distant light. Each photon is precise, each measurement repeatable. Yet collectively they describe a universe whose evolution is neither simple nor predictable. The light that reaches you is both a messenger and a contradiction, encoding history that is tangible, measurable, and profoundly counterintuitive. You begin to realize that the universe communicates in scales, durations, and sequences that are only partially accessible to your senses and instruments. The farther you look, the more you confront the limits of linear time as a descriptor of cosmic evolution. Light carries certainty, but it also carries dissonance, revealing a cosmos whose history cannot be fully reconciled with the temporal frameworks you carry from your room into the universe. In observing it, you encounter the scale of cosmic time itself, and the subtle, unsettling fact that the story it tells is stranger than intuition alone could ever suggest. Galaxies before their time. You expect early galaxies to be simple, small, diffuse. Observations confirm none of that. Fully formed, spiral, and elliptical systems appear when models predicted chaos, as if the universe compressed its maturation into the briefest intervals, violating your intuitive sense of temporal scale. In the earliest epochs, your understanding suggests matter should be scattered, coalescing gradually through slow, gravitational collapse. The first galaxies, in theory, should resemble loose clouds of gas with irregular shapes, minimal star formation, and little internal organization. Yet the data from James Webb reveals structures that are coherent, symmetric, and massive, already bearing the hallmarks of dynamical stability. The spirals you observe display organized rotational patterns. Arms curve elegantly, tracing orbits that imply sustained gravitational balance. Elliptical galaxies appear dense and spheroidal, indicating that they have already undergone processes of collapse, merging, and star formation. Light from these systems carries the chemical fingerprints of multiple generations of stars. The spectra indicate metals, carbon, oxygen, iron, produced in nuclear furnaces of stars that must have existed before the observed galaxy even formed. The timeline implied is compressed. Evolution has occurred with a rapidity that challenges the mechanisms you consider standard. Even the masses of these galaxies are unexpected. Some contain billions of solar masses, concentrated in cores that suggest early assembly of stellar populations and possibly central black holes. The very presence of these masses so soon after the Big Bang implies processes operating at speeds beyond what your models predict. Star formation rates, inferred from the light curves, are extreme, often exceeding the thresholds that simulations of early galaxy growth allow. In essence, the universe appears to have accelerated its development, forcing complexity into a span of time that seems insufficient by classical reasoning. Beyond individual galaxies, patterns in clustering and alignment hint at larger-scale organization emerging concurrently with the formation of the first stars. Cosmic filaments and protoclusters are traced in the distribution of these early systems. Gravity has sculpted structure on multiple scales, from the dense cores of galaxies to networks spanning millions of light years. The rapidity of this structure formation creates tension between local and global timescales. Processes internal to galaxies unfold at near maximal rates, while the broader cosmic framework develops in concert, producing a coherence that appears improbable under standard assumptions of gradual evolution. The implications extend further when considering feedback processes. Supernovae, stellar winds, and radiation pressure from early stars should disrupt nascent galaxies. Yet observations indicate that these galaxies retain structural integrity despite intense internal activity. They are simultaneously energetic and stable, turbulent yet ordered. Each photon arriving at your instruments carries evidence of both violent internal processes and sustained equilibrium. The universe seems to balance extremes, achieving maturity with precision and efficiency that defies naive expectation. Chemical enrichment adds another layer of complexity. The presence of metals implies multiple generations of star formation and destruction within a window of only a few 100 million years. The data suggests that stars were born, lived, and died in rapid succession, producing art and heavy elements that were then incorporated into the next generation. You confront a cosmos that is not leisurely. It is urgent, compressing vast evolutionary sequences into intervals that, by conventional understanding, should be insufficient for such outcomes. Ultimately, galaxies before their time confront the assumption that complexity requires duration. The light arriving now proves that the universe's earliest epochs were not uniformly primitive, but contained pockets of remarkable maturity. Measurement confirms what your intuition struggles to accept. Order and structure emerged almost immediately, as though the universe prioritized organization over gradualism. You are forced to question the linearity of cosmic evolution, to consider that the story of time itself may be uneven, punctuated, or emergent. Every photon from these galaxies is a record of acceleration, a challenge to expectation. Your models, simulations, and assumptions about early cosmic history are incomplete, unable to capture the rapidity with which matter formed, stars ignited, and galaxies coalesced. You begin to see the universe as both orderly and paradoxical, governed by familiar laws, yet unfolding on timescales that stretch your intuition. Galaxies before their time reveal a cosmos that is precise, observable, and fundamentally unsettling in its early maturity. The paradox of early structure. If galaxies appear mature almost immediately after the cosmic dark ages, something in your understanding of gravitational collapse, star formation, or matter distribution is incomplete. The paradox is not speculative. It arises directly from consistent measurements across multiple fields. Observations from James Webb, combined with earlier data from Hubble and other surveys, show a repeated pattern. Structures form earlier, faster, and more coherently than standard cosmology predicts. Each independent measurement confirms the same anomaly, leaving no ambiguity in the data. The universe, it seems, is operating on schedules your models struggle to account for. You consider gravitational collapse, the process by which diffuse matter condenses into stars and galaxies. In principle, it is a gradual phenomenon. Clouds of hydrogen contract under gravity, fragment, ignite, and evolve. Yet the galaxies you observe at redshifts above 10 exhibit masses and internal organization that imply collapse occurred far more rapidly. Their cores are dense, their rotational patterns established, and their star formation histories compressed into intervals that challenge the time scales imposed by physics as you understand it. Light from these systems carries the evidence of processes completed before conventional timelines would allow. Star formation itself compounds the paradox. The earliest galaxies emit light that indicates extensive populations of massive stars, many already evolved into supernovae or remnants. The chemical signatures reveal heavy elements that should require multiple generations of stellar birth and death. Each spectral line, each emission feature, is a timestamp that implies a sequence of events accelerated relative to the cosmic calendar. The universe seems to have bypassed intermediate stages of development, producing order without the expected interval of disorder, stability without the expected gestation of chaos, matter distribution, both within galaxies and across the cosmic web, further underscores the anomaly. Filaments and clusters are mapped at scales, implying coherent growth, yet the timing appears compressed. Dense regions contain galaxies already mature, while neighboring voids remain largely empty, indicating that structure formation is highly uneven. You measure this distribution with redshift surveys, gravitational lensing, and cosmic microwave background imprints, and each technique confirms the same paradox. The universe develops coherence before it should. Even supermassive black holes contribute to the puzzle. Observed in galaxies, less than 1 billion years old. Their masses often exceed 1 billion solar masses. Standard growth models, relying on accretion and merger rates, cannot account for such rapid accumulation. Yet the light, the motions of surrounding stars, and the gravitational effects all provide unambiguous evidence of their existence. You are forced to accept that extreme structures emerge far sooner than anticipated, implying that the mechanisms you consider fundamental may operate differently under early universe conditions. This paradox challenges a fundamental assumption that temporal progression is linear and uniform across processes. Observation reveals that some systems evolve at accelerated rates, while others follow slower, more conventional paths. The universe is heterogeneous in its maturation, suggesting that local conditions, density fluctuations, and initial perturbations can dramatically alter the pace of evolution. Measurement, not theory, dictates this conclusion. The implications extend beyond early galaxies. If the mechanisms of structure formation are faster and more efficient than predicted, then all cosmic chronologies are affected. Timelines for star formation, chemical enrichment, black hole growth, and galactic assembly must be reconsidered. You cannot ignore these discrepancies. They are embedded in the fabric of observation. The universe communicates a rhythm that is not uniform, that challenges your models, and that is precise in its irregularity. In confronting the paradox of early V structure, you realize that your intuitions about gradual development, cumulative complexity, and predictable timelines are limited. The universe does not necessarily unfold in the slow, sequential manner you assume. Observation alone dictates the reality. Mature galaxies, massive black holes, and chemically enriched stars all exist far earlier than expected. The paradox is not a problem of measurement. It is a feature of the cosmos itself, quietly recorded in the light traveling billions of years to reach your instruments. It is a subtle, unresolvable tension between expectation and reality, one that forces you to reconsider what early even means in a universe defined by its observations rather than by your assumptions. Dark matter, the invisible architect. You cannot see dark matter, but its gravitational influence shapes galaxies. Yet the distribution implied by the earliest observations suggests a scaffolding that should not exist yet, accelerating structure formation in ways your models struggle to reconcile. In every galaxy, the motions of stars and gas betray the presence of unseen mass. Rotation curves remain flat. Velocities persist at levels inexplicable by visible matter alone. Even in the most distant systems, observed by James Webb, the fingerprints of dark matter are unmistakable. Halos, already massive and coherent, guiding the assembly of baryonic matter into fully formed galaxies. Your intuition assumes a gradual accumulation. Small density fluctuations in the primordial universe collapse under gravity, progressively forming larger structures. Dark matter, interacting only gravitationally, is expected to seed this process slowly, its influence accumulating over hundreds of millions of years. Yet the earliest galaxies defy this expectation. The scaffolding implied by observations is already extensive. Dense halos exist when, by conventional timelines, they should still be forming, and their gravitational pull has already gathered gas, stars, and even supermassive black holes into coherent systems. Measurement confirms this repeatedly. Simulations based on standard cold dark matter models cannot reproduce the observed speed or scale of formation. The paradox deepens when considering spatial distribution. Dark matter does not distribute evenly. It concentrates in filaments and nodes, leaving vast voids in between. These early structures reveal a web that is both precise and extensive, connecting galaxies across millions of light years. Observed correlations between the positions of early galaxies and inferred dark matter halos suggest that the universe was remarkably efficient in structuring itself, far more so than models predict. The light you detect, filtered through these gravitational frameworks, confirms alignment, clustering, and motion consistent with a mature cosmic web existing almost immediately after the cosmic dark ages. Beyond galaxies, dark matter influences internal dynamics. Stellar velocities, orbital patterns, and rotational profiles all indicate that these early systems are stabilized by halos far more massive than expected for their age. The distribution of mass accelerates star formation, compresses gas clouds, and regulates feedback from early supernovae. Dark matter acts as an invisible architect, guiding processes that your models assume require longer timescales. Observation makes it clear. Structure emerges not through gradual chance, but under a framework already present, preformed, and effective. Even at cosmic scales, dark matter challenges your intuition about time and causality. Large clusters of galaxies, linked by extended filaments, already exhibit coherent dynamics that suggest a pre-established gravitational network. The uniformity of this scaffolding across vast distances implies that the universe's growth was coordinated, not merely local. The halos measured today via lensing and kinematic effects are remnants of an architecture that existed earlier than your models anticipated. Time, in this sense, does not dictate development. The distribution of unseen mass sets the tempo. The interplay between dark matter and luminous matter amplifies the paradox. Gas collapses into the potential wells defined by halos, stars ignite, and black holes grow. All processes accelerated by the invisible framework. Yet the same observations reveal that this framework is already extensive when it should still be assembling. You confront a subtle, persistent tension. The universe's early history is ordered, precise, and efficient in a manner that standard gravity-driven models cannot easily reproduce. Every measurement, from rotation curves to gravitational lensing, from chemical enrichment to galaxy clustering, points toward the same conclusion. Ultimately, dark matter reveals a universe operating under unseen constraints, guiding evolution without revealing its presence. The paradox is not that structures exist. It is that they exist with such maturity, such coherence, and such speed. Measurement, observation, and physics converge to show a cosmos whose development is scaffolded invisibly, accelerating formation and compressing what you assumed would require eons into mere hundreds of millions of years. The invisible architect is not speculation. It is recorded in the motion of stars, the light of galaxies, and the geometry of cosmic filaments. You begin to understand that the universe's hidden framework shapes every epoch you observe, quietly dictating the timing, scale, and pace of cosmic history long before the first photons reached your instruments. Redshift and the illusion of simplicity. Redshift maps distance and time, giving the universe a framework you can quantify. But when these distant galaxies show unexpected mass and metallicity at extreme redshifts, the simple story of a steadily expanding, gradually evolving cosmos fractures under observation. You rely on redshift as a tool to translate the stretch of light into temporal and spatial information. Light arriving from a galaxy billions of light years away has been elongated by the expansion of space. In principle, the higher the redshift, the earlier the epoch you observe. This mapping has long provided the scaffolding for cosmology, linking distance, velocity, and age in a predictable structure. Yet James Webb reveals a universe in which this framework is imperfect. Galaxies at extreme redshifts, Z values exceeding 10, already exhibit mass comparable to galaxies seen in much later epochs. Their stars are chemically enriched, indicating prior generations of stellar evolution. Metals are present in amounts that suggest repeated cycles of formation and destruction. In short, the timeline implied by redshift conflicts with the processes needed to produce these properties. The universe, as measured, is simultaneously young by redshift and mature by internal composition. The apparent linearity of time, so inherent in redshift-based reasoning, becomes an illusion. The problem deepens when considering star formation rates. Infrared observations indicate that some early galaxies have already converted a substantial fraction of their gas into stars. The luminosity observed, when translated into mass via established models, implies that the majority of these stars formed in intervals shorter than the available cosmic time at that redshift. You calculate the expected duration for such formation based on cooling rates, gravitational collapse, and feedback mechanisms. Observed values exceed these predictions. Redshift provides a temporal marker, yet the evolutionary processes traced by light appear accelerated, compressed, and counterintuitive. Metallicity complicates the picture further. Heavier elements are produced in stars and dispersed through supernovae. Their presence in galaxies at extreme redshift indicates that multiple stellar generations preceded the epoch you are measuring. This implies a cycle of formation, evolution, and death occurring at velocities that challenge conventional physics. The light you observe is precise, the spectra repeatable, yet the story it tells cannot be reconciled with the simple chronological order suggested by redshift. Space and time, once treated as linear frameworks, now exhibit hidden complexity. You also observe that not all galaxies evolve uniformly. Some high redshift systems remain small, irregular, and low in metallicity, while others have already achieved structural and chemical maturity. The illusion of simplicity arises when redshift is treated as a straightforward measure of age. In reality, it encodes a combination of distance, expansion rate, and historical processes that may vary significantly between regions. Two galaxies with identical redshifts can differ dramatically in mass, composition, and development. Measurement exposes heterogeneity on a scale that defies expectation, showing that cosmic evolution is neither uniform nor predictable. Gravitational lensing further complicates interpretation. Light from high redshift galaxies is bent and amplified by intervening mass, altering apparent brightness, structure, and size. You must carefully account for these distortions to reconstruct intrinsic properties. Even when corrected, the early universe continues to show anomalies in mass distribution and chemical composition. Redshift provides a map, but the territory it charts is uneven, intricate, and at times paradoxical. Ultimately, the illusion of simplicity dissolves when observations at extreme redshift are taken seriously. The universe does not unfold in a gradual, linear fashion. Its early history contains pockets of rapid growth, accelerated chemical evolution, and massive structural formation. Redshift remains an indispensable tool, but it is no longer a guarantee of temporal intuition. Each photon is a record, precise yet subtly dissonant, revealing a cosmos whose evolution is layered, heterogeneous, and far more complex than the straightforward expansion your models once suggested. You are left with a quiet tension. Redshift offers clarity and measure, but also conceals the universe's uneven rhythms. The farther you look, the more the early universe defies expectation. Light tells a story that is both true and incomplete, precise yet paradoxical, revealing the subtle ways in which your framework of time and distance can mislead even as it measures. The speed of formation. Star clusters, supermassive black holes, and galactic cores appear almost instantaneously relative to cosmic timelines. Measurements of stellar populations imply formation rates that exceed the limits predicted by cooling and collapse physics. The universe in these early epochs seems impatient. You expect matter to condense gradually, gas clouds slowly collapsing under gravity, fragments cooling and coalescing over millions of years. Yet observations reveal dense stellar populations emerging with a speed that contradicts conventional models, suggesting that the processes responsible for star and galaxy assembly operate on timescales far shorter than previously assumed. The James Webb Space Telescope captures light that originated in the first few 100 million years after the Big Bang. Within that light is encoded evidence of stellar systems that are already mature, containing stars massive enough to have completed life cycles and enriched their surroundings with heavy elements. Clusters of stars, forming in unison, exhibit mass and density profiles that imply extremely efficient cooling and condensation mechanisms. The photons you receive confirm these populations exist, but your calculations indicate that the time available for such processes should be insufficient. Light, in effect, reveals a universe working at maximum capacity. Supermassive black holes present an even starker contradiction. Observed at redshifts corresponding to less than 1 billion years after the Big Bang, they possess masses of hundreds of millions or even billions of solar masses. The conventional pathways, accretion, merger of smaller black holes, cannot produce such masses so quickly without invoking extreme and unobserved efficiencies. The surrounding stellar populations, revealed through spectral analysis, indicate that the black holes did not grow in isolation. Their mass is intertwined with the rapid assembly of galactic cores. Observation alone dictates that these systems reached maturity at a pace that your models consider improbable, if not impossible. Star formation rates, measured in these early galaxies, confirm the same pattern. Infrared luminosity, combined with chemical abundance, suggests bursts of star formation intense enough to produce massive populations in mere tens of millions of years. Cooling physics, fragmentation rates, and gas dynamics impose strict upper limits on how fast such bursts could occur. Yet the light you measure exceeds these limits. The universe, as recorded in these photons, has condensed matter into complex systems almost immediately after the cosmic dark ages, defying expectations of a slow, incremental evolution. The speed of formation also has implications for galactic morphology. Spirals and elliptical systems are already distinct, exhibiting ordered rotation and internal structural coherence. Stellar feedback, winds, radiation, and supernova that should disrupt fragile early galaxies does not prevent them from achieving stable configurations. The observations imply that formation and stabilization were nearly simultaneous, compressing processes you assumed would be sequential into overlapping intervals. Each photon carries evidence of this acceleration, showing systems that are energetic yet organized, turbulent yet stable. Even chemical evolution is accelerated. Heavy elements are present in abundance, suggesting multiple generations of stars already completed their life cycle. Dust, produced in stellar deaths, is incorporated into subsequent star formation with remarkable efficiency. These cycles, which normally require hundreds of millions of years, appear to have occurred within the first few 100 million years, implying a cosmic clock operating at an unexpected pace. Observation leaves no alternative. The universe, in its earliest epochs, proceeds faster than your models predict, in a manner measured and precise. Ultimately, the speed of formation confronts your assumptions about temporal order. Time, as you experience it locally, unfolds gradually and predictably. Across cosmic distances, however, the emergence of complex structures is rapid, punctuated, and uneven. Stellar populations, black holes, and galactic cores do not grow sequentially at leisurely rates. They appear almost instantaneously, accelerated by forces and mechanisms encoded in the universe itself. Measurement reveals a cosmos that is precise, consistent, and deeply counterintuitive, a universe impatient to form the first structures, yet doing so in ways you can observe and quantify. You are left with a subtle unease. The early universe does not unfold at the pace your intuition assumes. Light and gravitational influence testify to systems that emerge fully formed, organized, and chemically mature in a fraction of the time your models permit. The speed of formation is not an artifact of error. It is a fundamental property of the cosmos, quietly documented across billions of light years, forcing you to reconcile the limits of physics with the urgency of cosmic evolution. Unexpected metallicity. The earliest galaxies show chemical enrichment levels that implied generations of stars lived and died before they could have existed. Your models, grounded in nuclear fusion timescales, cannot easily explain this. Observation imposes a contradiction: maturity without sufficient elapsed time. In principle, elements heavier than helium, carbon, oxygen, iron, are produced exclusively in the cores of stars and released into the surrounding medium during supernova explosions. This process, by necessity, requires multiple stellar life cycles. Yet when James Webb measures the spectra of galaxies at redshifts exceeding 10, you detect metals in abundances that imply these cycles have already occurred, long before conventional models allow for the evolution of sufficient numbers of stars. The problem begins with timescales. Massive stars evolve quickly, in tens of millions of years, yet they require time to form from gas clouds, cool sufficiently, and ignite nuclear fusion. Intermediate mass and low mass stars evolve far more slowly, on scales of hundreds of millions to billions of years. The early universe, at the redshifts you are observing, exists in periods that are barely enough to accommodate even a single generation of massive stars. Yet the observed metallicity implies that multiple generations have already contributed to the chemical composition of the interstellar medium. Measurement forces the conclusion. The universe has compressed evolutionary processes into a window that your models predict should be insufficient. The consequences are evident in the stars themselves. Populations of early galaxies show not only metals, but also uniform distributions of these elements across their cores. This implies efficient mixing, dispersal, and incorporation of enriched material into subsequent star formation. Gas clouds have undergone collapse, ignition, death of stars, and redistribution of heavy elements with extraordinary rapidity. Spectral lines reveal oxygen, carbon, and iron in ratios that mimic later, more mature galaxies. The photons arriving at your instruments encode histories that suggest an accelerated chemical evolution, a speed of enrichment that standard nuclear physics struggles to accommodate. Supernovae further complicate the narrative. The energy released in early explosions should disrupt nascent galaxies, dispersing gas and inhibiting subsequent star formation. Yet these early systems retain structural integrity while simultaneously showing evidence of chemical recycling. You measure stellar populations in these galaxies and see that enrichment has occurred without wholesale destruction. The early universe, it appears, is capable of balancing violence with order, creating mature chemical environments almost immediately after the first stars form. The presence of metals also influences subsequent evolution. Cooling rates depend on chemical composition. Enriched gas collapses more efficiently, accelerating star formation. You observe galaxies in which rapid chemical enrichment has likely sped up the assembly of stars and galactic cores, creating a feedback loop that further compresses timescales. Observation and measurement reveal this process, demonstrating that metallicity is not simply a passive byproduct, but a factor actively shaping the speed and structure of early galaxy formation. Even at larger scales, metallicity hints at unexpected maturity. Clusters and proto-clusters of galaxies show correlated enrichment, suggesting that the dispersal of metals is coherent across vast distances. Light from these galaxies, filtered through intervening space, confirms that the chemical evolution of the universe is uneven, yet surprisingly efficient. The distribution of heavy elements implies a universe that has already undergone significant processing, even when standard timelines indicate it should still be in its infancy. Ultimately, unexpected metallicity forces a reconsideration of cosmic chronology. Light, spectra, and chemical signatures combine to tell a story in which maturity precedes expectation. Stars live, die, and enrich their surroundings faster than nuclear physics and cosmological models would predict. Observation imposes a contradiction. Galaxies exist that are chemically complex before the universe has elapsed the time required for such evolution. Measurement leaves no ambiguity. The early cosmos operates on accelerated rhythms, compressing the processes you assume require eons into intervals that are observable, measurable, and fundamentally unsettling. You are confronted with a quiet paradox. The universe is chemically mature before it should be, precise in its enrichment, and efficient in its recycling. Metallicity, like mass and structure, demonstrates that the cosmos does not unfold according to the timelines your intuition suggests. Every photon carries the imprint of this accelerated evolution, forcing recognition that time, as measured by chemical processing, is not always what it seems. Black holes, too early. Supermassive black holes, millions or billions of solar masses, exist at epochs when their growth should be physically impossible. The James Webb observations confirm their presence, forcing a reconsideration of growth mechanisms and temporal expectations across cosmic history. In your conventional understanding, black holes form from the collapse of massive stars. These stellar remnants then grow gradually, accreting matter and merging with other black holes over hundreds of millions, even billions of years. Yet the earliest systems you now observe challenge this logic. Colossal black holes exist when the universe is only a few 100 million years old, far too soon for the processes you rely upon. The first clue comes from their gravitational influence. Stars in the surrounding galaxies orbit at velocities that imply a central mass far greater than any visible material could produce. Light from the accretion disks surrounding these black holes emits intensely in X-ray and infrared bands, revealing both mass and energetic output. Measurement of this light, combined with dynamical modeling, confirms that these black holes have reached masses of hundreds of millions of solar masses, sometimes exceeding 1 billion. According to standard accretion physics, such growth would require more time than the universe has existed at the observed redshift. Observation leaves no ambiguity. These objects are real, massive, and mature. Even the simplest models of black hole growth fail to account for the data. Accretion rates are limited by the Eddington threshold, the balance between radiation pressure and gravitational pull, which constrains how quickly matter can fall into a black hole. Exceeding this threshold leads to self-limiting effects. Radiation expels infalling gas, slowing growth. Yet the early black holes you detect imply growth that approaches or surpasses these theoretical limits, sustained over hundreds of millions of years or less. The implication is inescapable. Either the growth mechanism is fundamentally different in the early universe, or the initial seeds were already extraordinarily massive. The paradox deepens when considering the relationship between black holes and their host galaxies. In mature systems, black hole mass correlates with stellar mass and velocity dispersion in the galactic bulge. Observations of high redshift galaxies show the same correlations, even when the timescales available for coevolution are minimal. Black holes have achieved substantial mass, while their surrounding galaxies are only partially assembled, implying that growth can outpace or occur independently of galactic evolution. The universe, in these early epochs, seems capable of producing extreme systems in parallel rather than sequentially. Formation theories, such as direct collapse of massive gas clouds or runaway mergers in dense clusters, offer potential explanations, but they carry their own limitations. Direct collapse requires conditions that are rare and precise. Gas must avoid fragmentation, cool efficiently, and collapse almost symmetrically. Runaway mergers demand extreme stellar densities and improbable initial configurations. Yet observations suggest that early supermassive black holes are not anomalies. They are present in multiple, widely separated systems. Measurement confirms that these growth pathways, however improbable in theory, must have operated effectively in the early cosmos. Even more striking is the chemical and structural environment surrounding these black holes. Their host galaxies show evidence of metallicity, star formation, and energy feedback that indicate complex histories compressed into extraordinarily brief intervals. The accretion of matter, formation of stars, and enrichment of interstellar gas are all occurring on overlapping timescales, creating mature, energetic systems far earlier than intuition or classical models predict. Each photon, each spectral line, each gravitational signature records a cosmos working at maximal efficiency. Ultimately, black holes too early confront your assumptions about the pace of cosmic evolution. You are forced to recognize that the universe can assemble extremes, massive singularities, chemically enriched galaxies, coherent galactic structures, in intervals previously considered insufficient. Observation imposes a direct contradiction. The early universe is both physically constrained and remarkably capable, operating on rhythms that your models cannot easily accommodate. The presence of these black holes is not speculative. It is measured, repeatable, and profoundly unsettling. You are left with a quiet, persistent unease. Time, as you perceive it, is not the definitive measure of development. Supermassive black holes appearing far too early demonstrate that the universe has mechanisms for rapid assembly and extreme acceleration, encoded in the fabric of matter, gravity, and energy. Measurement confirms their reality. Intuition cannot fully account for their existence. The early cosmos, it seems, is both precise and paradoxical. Cosmic inflation and its limits. You understand inflation as a rapid stretching of space, setting initial conditions. Yet the structures observed at extreme distances strain even the generous allowances of inflationary theory, suggesting that the seeds it planted grew faster or differently than your calculations allow. In the standard picture, inflation magnifies quantum fluctuations, producing the slight density variations that later collapse under gravity to form galaxies and clusters. These perturbations are small, uniform, and statistically predictable. Measurement of the cosmic microwave background confirms their presence, and simulations based on these initial conditions reproduce the large-scale distribution of matter reasonably well at later epochs. Yet, when you examine galaxies at redshifts above 10, the patterns challenge these predictions. Fully formed systems appear in regions where the initial fluctuations should have been insufficient to produce coherent structures so quickly. Stellar populations, metallicity, and black hole growth all indicate that the early universe has amplified its primordial seeds into complex structures far more rapidly than standard models suggest. Measurement confirms this not as an anomaly, but as a recurring feature across multiple observations, implying that the inflationary framework, while accurate in describing general large-scale properties, does not fully explain the pace or scale of early evolution. The paradox becomes evident when considering mass distribution. Inflation predicts a roughly Gaussian spectrum of density fluctuations. High-density regions should collapse first, forming small protogalaxies, with larger systems emerging only through mergers over extended timescales. Observations contradict this hierarchy. Massive galaxies and supermassive black holes appear contemporaneously, implying that the initial perturbations were either larger than expected, or that growth proceeded faster than allowed by gravity, cooling, and feedback physics. You measure the light from these systems, calculate their mass, and consistently find maturity incompatible with the available elapsed time. Even the cosmic web, the vast network of filaments and voids, amplifies the tension. Simulations seeded with standard inflationary fluctuations produce filamentary structures on roughly correct scales, but they form more slowly than the observations indicate. Protoclusters and aligned filaments at extreme redshifts imply coordinated collapse across millions of light years in intervals that seem insufficient under standard gravitational evolution. Observation demonstrates coherence, yet the universe has not yet existed long enough, according to conventional timelines, for such large-scale structures to assemble. Chemical evolution further strains expectations. Metals, dust, and heavy elements appear in regions predicted to be chemically primitive. Inflation seeds. Fluctuations in matter density, not chemical composition, yet the observational record shows that these early overdense regions rapidly evolve, producing multiple generations of stars and enriching their surroundings with heavy elements. Light from these galaxies encodes evidence of accelerated processing, suggesting that the mechanisms converting primordial density fluctuations into structured, chemically evolved systems are more efficient than standard inflationary models allow. Even rare processes, such as direct collapse, black holes, or rapid star cluster formation, do not fully resolve the discrepancy. Inflation sets the stage, but the universe appears to operate with a speed and coordination that exceed the initial conditions it provides. The photons you measure carry evidence that the early cosmos, while consistent with the statistical predictions of inflation on large scales, manifests maturity, complexity, and organization on local scales far earlier than expected. Ultimately, cosmic inflation provides a framework, but not a full account of the early universe's behavior. Measurement, not speculation, reveals that while inflation seeded structure, the growth of these seeds is faster, more coordinated, and more efficient than your models predict. You are confronted with a universe in which the initial conditions, while seemingly simple and uniform, have been amplified in ways that challenge your understanding of time, growth, and causality. The limits of inflation are exposed not through theoretical failure, but through the precision of light traveling across billions of years, quietly revealing a cosmos that is orderly, measurable, and unexpectedly accelerated. You are left with the subtle disquiet that even the most foundational mechanisms in cosmology, designed to explain the universe's initial state, do not fully account for the rapid emergence of the structures you observe. Inflation sets the stage, but the performance you witness proceeds at a tempo that defies expectation, recorded precisely in the earliest light reaching your instruments. Hubble tension amplified. You have relied on the Hubble constant as a measure of expansion rate. Yet early universe measurements, implied by JWST data, intensify the already known Hubble tension, showing that different methods of measuring expansion produce conflicting but precise values. Local measurements, using Cepheid variables and type 1, a supernovae, indicate one rate of expansion. Observations of the cosmic microwave background, extrapolated through lambda CDM cosmology, indicate another. Both are internally consistent, both precise, yet they diverge beyond expected statistical error. The universe, as measured, refuses to conform to a single temporal scale. JWST deep field observations introduce additional data points into this discrepancy. Galaxies at extreme redshift provide independent measures of expansion, inferred from luminosity distances, redshift, and inferred age of stellar populations. When these measurements are compared with local and CMB-derived rates, the divergence grows. The universe's expansion appears to be both faster and slower, depending on the observational method. The light you measure, carrying the imprint of billions of years of cosmic history, records a reality in which temporal progression is not uniform. This conflict is more than an anomaly. It is reinforced by multiple independent techniques. Gravitational lensing, baryon acoustic oscillations, and supernova surveys all provide data consistent with their respective expansion rates, yet incompatible with each other. Each method is precise, repeatable, and grounded in well-understood physics. No single error, no uncorrected bias can fully account for the divergence. Measurement itself imposes the contradiction. The universe simultaneously supports multiple mutually inconsistent clocks. The paradox extends into cosmology's predictive models. The Hubble constant is foundational in converting redshift into cosmic time, in estimating galaxy ages, and in modeling large-scale structure formation. If different methods yield different expansion rates, then timelines derived from redshift are ambiguous. Galaxies that appear young under one calibration may be comparatively older under another. Stellar populations, chemical evolution, and black hole growth are all sensitive to these timelines. Measurement reveals that your assumptions about uniform temporal progression across the cosmos may be invalid, even in a framework of highly precise physics. The tension also suggests deeper complexity in the universe's expansion history. You have assumed a smooth, homogeneous expansion driven by dark energy and matter density. Yet the early appearance of massive, chemically enriched galaxies, the rapid growth of black holes, and the unexpectedly mature cosmic web all imply local acceleration or variability inconsistent with a single global rate. The Hubble tension is not simply a discrepancy in numbers. It is a reflection of the universe's heterogeneous temporal unfolding, encoded in light, gravity, and structure itself. Even the physical mechanisms that might reconcile the tension are speculative, and none are directly confirmed by observation. Some invoke new physics, early dark energy, modifications of general relativity, or unknown interactions in the primordial universe. None are necessary to describe the measurements themselves. Observation alone is sufficient to show the divergence, the inability of a single Hubble parameter to capture the universe's expansion history. The data is precise, the contradiction persistent, and the implication clear. Temporal measurement is context-dependent. Ultimately, Hubble tension amplified by JWST data forces you to confront an unsettling truth. The cosmos does not yield a single, consistent measure of time or expansion. Light from distant galaxies, combined with local measurements and CMB inferences, presents a reality in which the pace of cosmic evolution is ambiguous, heterogeneous, and subtly inconsistent. Each method is valid, yet collectively they reveal a universe that cannot be fully reconciled under a single temporal framework. You are left with the quiet unease that the universe's history is not universally calibrated. Expansion, the metric by which you interpret redshift, distance, and age, does not march uniformly. The cosmos, as measured, is simultaneously precise and paradoxical, resisting the simplicity of a single Hubble constant while revealing the complex and uneven tempo of cosmic time. Time as a local approximation. Observations suggest that time may not be uniform across the universe in the way you imagine. Measurements of early cosmic epochs imply local rates of evolution that diverge from global averages, challenging the assumption that a universal cosmic clock exists. You have long assumed that redshift, expansion, and distance collectively define a single temporal progression, a cosmic timeline that applies equally to all matter. Yet the galaxies you observe at extreme redshift tell a different story. They mature, evolve, and chemically enrich themselves at rates that are inconsistent with the intervals suggested by the average expansion of space. The paradox emerges when comparing regions of the early universe. Some proto-galaxies, observed at identical redshift, display mature spiral or elliptical morphologies. Stellar populations are chemically enriched. Supermassive black holes already dominate galactic cores, and star formation is intense but orderly. Nearby regions at the same redshift remain diffuse, irregular, and chemically primitive. The implication is that local evolution is heterogeneous. Time, as inferred from development, does not advance uniformly across space. You measure these differences repeatedly, and each observation confirms that what you perceive as a single epoch is in fact a mosaic of temporal rates. Redshift, traditionally your tool for mapping time, becomes a local rather than universal measure. It faithfully encodes the expansion of space between you and the source, yet it does not directly dictate the pace of structure formation within that source. Galaxies can evolve faster or slower than redshift would imply, depending on local density, gravitational interactions, dark matter concentration, and initial conditions seeded by inflation. The cosmic clock you assumed was universal is revealed as an approximation, useful for large-scale averages, but insufficient for interpreting the rhythms of individual systems. This perspective gains weight when considering chemical evolution. Heavy elements required for cooling, star formation, and planet building appear in some regions almost immediately after the first generation of stars. In other regions, the same redshift corresponds to near pristine hydrogen and helium. The same cosmic time, as measured globally, contains intervals of rapid, extreme evolution alongside regions of delayed development. Observation confirms that time, in this context, is a locally emergent property. It is defined not by universal constants alone, but by the conditions, interactions, and histories of individual systems. Even black hole growth underscores the same pattern. Supermassive black holes in certain proto-galaxies reach hundreds of millions of solar masses, while neighboring systems of comparable age show only modest stellar remnants. Their evolution is decoupled from a single, uniform temporal scale, implying that local environmental factors govern the pace of collapse, accretion, and energy feedback. Light from these systems encodes the record of accelerated local histories, demonstrating that global averages obscure the diverse tempos at which structure emerges. Gravitational lensing, dark matter distribution, and cosmic filaments further reveal temporal heterogeneity. Denser regions collapse faster, amplifying growth rates, while voids remain underdeveloped. The universe's expansion stretches space, but the internal evolution of matter within that space does not adhere to a single clock. Each photon carries a history shaped by both local gravitational conditions and cosmic expansion, resulting in a complex overlay of rates that measurement can detect, but intuition struggles to reconcile. Ultimately, time as a local approximation reframes your understanding of cosmic history. Redshift, expansion, and distance provide a framework. But evolution within that framework is uneven, context-dependent, and locally accelerated or delayed. Observation demonstrates that the early universe does not unfold according to a single global chronology. Instead, it proceeds at multiple overlapping tempos, each system following its own rate while still constrained by fundamental physics. Measurement records these discrepancies unambiguously. The universe's temporal landscape is heterogeneous, precise, and quietly unsettling. You are confronted with a subtle disquiet. The cosmic clock you rely upon is approximate, emergent, and locally variable. What you perceive as uniform time is, in reality, a patchwork of rates, each measured and real. The universe has rhythms that cannot be reduced to a single number, revealing the limits of intuition and the intricate, uneven unfolding of cosmic history. The cosmic horizon. You trust that the observable universe contains all you can measure. But the more you measure, the more you encounter structures near the horizon that suggest correlations beyond causal reach, hinting at a scale of order and interaction that defies conventional timelines. The observable universe is defined by the distance light has traveled since the Big Bang, creating a limit beyond which you cannot directly detect matter. Within this boundary, every galaxy, cluster, and filament is accessible to measurement. Yet even here, the patterns you detect imply connections that should be impossible given the finite speed of light and the time available for interaction. Large-scale surveys reveal unexpected coherence. Filaments of galaxies stretch across hundreds of millions of light-years, their orientations and densities correlated in ways that are statistically improbable under standard lambda CDM cosmology. The cosmic microwave background provides additional evidence. Temperature fluctuations and polarization patterns show correlations across angular scales that, according to naive causal arguments, should never have interacted. Measurement confirms these correlations repeatedly, indicating that distant regions, seemingly beyond each other's causal horizon, share properties and structures as if they had been coordinated. The paradox is amplified when you consider early galaxies. JWST observes mature galaxies near the edge of the observable universe, whose assembly implies interaction, merger history, and gas accretion that could only occur if large-scale coherence existed from the outset. The very light that defines the horizon carries the record of processes that should be isolated by distance and time. Yet these systems exhibit structural and chemical properties suggestive of coordinated evolution. Observation suggests that the universe's formative processes operate on scales far larger than the causal limits implied by simple light travel arguments. Dark matter further complicates this picture. The inferred distribution of invisible mass indicates a scaffolding of filaments and nodes extending to the limits of observation. These structures appear connected, aligned, and mature, guiding the formation of luminous matter across vast distances. Yet according to standard cosmology, there has not been sufficient time for matter to collapse coherently over such scales. Measurement provides no room for speculation. Gravitational lensing, galaxy clustering, and velocity mapping all reveal patterns that should not exist given the finite causal horizon. Even the statistical distribution of galaxies challenges intuition. Surveys show regions of overdensity and voids whose sizes exceed the expected scales of initial density fluctuations. The probability of such large, coherent regions arising randomly is vanishingly small, yet they are present. The observable horizon, rather than delimiting isolated islands, contains structures whose alignment implies processes operating beyond conventional causal limits. Observation imposes a constraint. The universe is coherent at scales you would expect to be disconnected. Cosmic expansion further complicates interpretation. Regions near the horizon recede at velocities approaching the speed of light relative to you. Their light encodes information from epochs when they were already distant, yet their properties correlate with nearer structures in a manner that suggests a larger, unified process. The observable horizon, in this sense, is not simply a boundary of ignorance. It is a region in which measured correlations hint at a deeper, unseen order, stretching beyond the time available for causal interaction. Ultimately, the cosmic horizon forces a subtle unease. You are confronted with a universe in which local measurement, large-scale structure, and statistical alignment suggest coherence beyond what should be possible. Light from the farthest galaxies and cosmic background radiation reveals correlations that transcend the apparent limits of causality. Observation, not theory, dictates the paradox. The universe possesses order at scales where time and light should prevent it. You are left with a quiet tension. The observable universe, the very limit of what can be measured, hints at a reality that extends in both scale and coordination beyond your causal grasp. Every photon from near the horizon encodes evidence of processes and structures that challenge your assumptions about isolation, interaction, and temporal progression. Measurement insists upon coherence, and coherence persists where it should not exist. The horizon, it seems, is not a boundary of isolation, but a reminder of the vast, ordered, and mysterious expanse that lies beyond what you can see. Gravitational lensing and hidden, time mass bends light, revealing objects otherwise invisible. Through lensing, you see galaxies that predate your expectations, as if the universe's growth occurred on a schedule independent of simple cause and effect. Gravitational lensing arises from the curvature of space-time around massive objects, altering the paths of photons and magnifying distant sources. This effect allows you to detect galaxies that would otherwise be too faint, too small, or too distant to observe directly. Measurement through lensing thus provides access not only to hidden structures, but also to timelines that challenge conventional expectations. Lensed galaxies at extreme redshifts often appear both massive and chemically mature, suggesting that formation processes occurred faster than your models permit. Their light encodes a history of star formation, accretion, and chemical enrichment, all compressed into intervals that seem insufficient given the available cosmic time. You measure the distribution of lensed images, calculate intrinsic luminosities and masses, and find consistency across multiple systems. Early galaxies are mature, dense, and well-structured. Lensing does not fabricate these properties, it reveals them. The universe, in effect, exposes its accelerated history, providing a record of events that, by conventional timelines, should not yet exist. The bending of light also creates multiple images of the same object, often magnified and displaced across the sky. Each image arrives along a different path, traversing varying gravitational potentials. These time delays encode subtle differences in the perceived evolution of the source, allowing you to probe the relative pacing of formation across paths. Measurement shows that even accounting for lensing geometry, the objects appear older and more developed than expected. Observation becomes a direct probe of hidden chronology. The universe's record, encoded in photons traveling along curved paths, reveals that local evolution can outpace what a simple linear timeline would suggest. Lensing also uncovers mass that is otherwise undetectable, including dark matter. By analyzing distortions in the shapes of background galaxies, you map the unseen scaffolding that shapes visible structures. These dark matter halos exist at scales and densities that imply rapid assembly. The distribution of mass accelerates the evolution of baryonic matter, guiding star formation, galactic morphology, and black hole growth. Observation shows that hidden mass not only affects spatial structure, but also temporal progression. The universe's growth is coordinated through a network of matter whose influence is invisible until measured via lensing. Time, in this sense, is emergent and locally amplified by the unseen. Even on the largest scales, lensing suggests coherence beyond expectation. Galaxy clusters act as natural telescopes, revealing distant systems whose light originated near the cosmic dawn. These lensed systems are not random. Their properties correlate with the mass distribution of the intervening lens. Observation demonstrates that the early universe is organized in ways that accelerate formation and create synchronized development across regions that, under simple causal assumptions, should be independent. Measurement through lensing exposes a hidden temporal order, a chronology that is obscured in direct observation, but revealed through the gravitational record. Ultimately, gravitational lensing transforms the act of measurement into a study of time itself. Light, bent and delayed, carries a record of processes that occurred in the early universe, often preceding what you would expect from simple extrapolation of cosmic expansion. The universe's hidden chronology, encoded in magnified, distorted, and duplicated images, shows that evolution is not uniform, that time can be locally accelerated, and that mass, both visible and invisible, acts as a mediator of cosmic pacing. Observation, precise and repeatable, reveals a universe in which the flow of events is more complex than the simple linear timeline you assumed. You are left with the subtle disquiet that even light, the most direct messenger from distant epochs, records histories that appear too mature, too rapid, and too coordinated. Gravitational lensing exposes not only structures beyond visibility, but also hidden temporal dynamics, forcing recognition that the universe's chronology is intricate, locally variable, and quietly unsettling. Measurement alone dictates the paradox. Time, as revealed through mass and light, is both real and subtly distorted, exposing the hidden order of the cosmos. The maturity of void. Galaxies. Galaxies, in sparse regions, isolated from major gravitational influences, already show complexity. Their existence implies processes that operate outside the mechanisms you associate with cosmic nurturing, suggesting time may be distributed unevenly across space. You expect isolated galaxies far from dense filaments and massive clusters to form slowly. Without the compressive effects of gravity from nearby structures, gas clouds should collapse more gradually. Star formation should proceed intermittently, and chemical enrichment should lag behind more crowded environments. Yet observations contradict these expectations. Void galaxies at high redshift already possess ordered structures, mature stellar populations, and significant metallicity. Spectroscopic analysis confirms that these galaxies are not anomalies. Light from their stars indicates multiple generations of formation, chemical recycling, and even early supernova activity. Metals are present in amounts comparable to galaxies embedded within dense cosmic filaments. Star clusters appear organized, and rotation curves suggest gravitational coherence sufficient to maintain stable disks or central bulges. Measurement leaves no ambiguity. These isolated systems are mature, chemically enriched, and structurally coherent, despite the absence of nearby gravitational scaffolding that, according to standard models, should drive and accelerate growth. The paradox deepens when considering their formation timescales. Void galaxies exist at redshifts corresponding to periods only a few 100 million years after the Big Bang. Conventional cooling, fragmentation, and star formation physics indicate that such systems should remain diffuse and irregular at these epochs. Observed maturity implies that these processes were accelerated locally, proceeding independently of the global density field. Measurement reveals that evolution in cosmic voids is not merely delayed. It is unexpectedly rapid, suggesting that local conditions or unknown mechanisms compress the development of structure in regions thought to be quiescent. Even black hole activity challenges expectations. Some void galaxies host central black holes of significant mass, whose growth requires both accretion and potential mergers. In isolation, these processes should be limited by the scarcity of surrounding matter. Yet light from these systems indicates active nuclei, with masses implying formation and growth rates that rival galaxies in dense environments. Observation demonstrates that maturation can occur without external assistance, implying that cosmic processes are not strictly dependent on environment or interaction, but can proceed with intrinsic efficiency. Chemical complexity also defies expectations. The presence of oxygen, carbon, and iron in these galaxies shows multiple cycles of stellar birth and death, with dust and metals incorporated into successive generations. Feedback processes, typically disruptive in small systems, have not prevented organized formation. Light encodes the record of early stellar evolution, confirming that isolated regions achieve maturity without the usual external catalysts. Measurement shows that even where gravitational scaffolding is weak or absent, time operates locally in ways that allow rapid evolution, revealing a non-uniform distribution of cosmic chronology. These observations force reconsideration of the underlying assumptions about time and causality. If isolated galaxies can mature rapidly while other regions evolve more slowly, then temporal progression is context-dependent, mediated by local physics, mass distribution, and perhaps as yet unidentified processes. Time is no longer a universal parameter. It is emergent, heterogeneous, and encoded in the specific histories of each system. The universe, as measured, contains overlapping tempos, with some regions accelerating, others lagging, and all coexisting within a single observable epoch. You are left with a subtle, persistent unease. Void galaxies demonstrate that structure, chemical evolution, and gravitational organization can emerge independently of expected drivers, suggesting that the universe's temporal landscape is uneven. Light from these systems records histories that are compressed, accelerated, and locally governed, showing that cosmic time is not uniform, but distributed across space in a complex, measurable pattern. Observation confirms the paradox. Isolation does not imply delay, and the universe's chronology is far more intricate than the linear progression you assumed. Cosmic star formation. Rates. You anticipate gradual ramp-up in star formation. Instead, early galaxies exhibit bursts of activity that imply temporal compression, as if entire stellar populations emerge simultaneously. Observations from JWST reveal galaxies at redshifts corresponding to a few 100 million years after the Big Bang, already hosting thousands to millions of stars, chemically enriched and distributed across coherent structures. Light from these galaxies indicates intense ultraviolet and infrared emission, a direct consequence of massive young stellar populations igniting nearly in unison. Measurement confirms that star formation is neither slow nor are incremental in these regions. It is rapid, episodic, and efficient. The timescales implied by these bursts challenge the standard physics of gas cooling and collapse. Molecular clouds require time to shed thermal energy, fragment into cores, and initiate nuclear fusion. Even with optimal densities, these processes unfold over tens of millions of years for massive stars. Yet, in observed early galaxies, the inferred age spreads of stellar populations are remarkably narrow. Spectral analysis reveals uniformity in composition and age that implies nearly simultaneous formation, compressing what you expect to be sequential processes into overlapping intervals. Observation leaves no room for adjustment. Star formation occurs at a pace that your models consider improbable. The bursts are not isolated phenomena. Multiple galaxies in the same field exhibit synchronized episodes of star formation, suggesting that this temporal compression is not a local anomaly, but a recurring feature of early cosmic history. Infrared luminosity measurements show that some galaxies convert gas into stars at rates approaching tens to hundreds of solar masses per year, vastly exceeding the rates expected from simple collapse and feedback models. Supernova feedback, which ordinarily regulates star formation by expelling gas, appears insufficient to slow these bursts. Measurement indicates a universe capable of reducing intense stellar activity before standard processes could have regulated it. Chemical signatures reinforce the paradox. Metals are present in proportions consistent with multiple prior generations of stars. Yet the total time available is shorter than required for such cycles under standard nuclear lifetimes. Dust produced in early supernovae is rapidly incorporated into subsequent star formation, allowing cooling and fragmentation to proceed efficiently. Light from these galaxies carries the evidence of rapid chemical recycling, showing that bursts of star formation are not only compressed temporally, but are also chemically sophisticated. Observation documents the simultaneous acceleration of both stellar mass assembly and enrichment, revealing a universe operating at maximal efficiency. Even the spatial distribution of star formation contributes to the paradox. Stars are organized into clusters, disks, and protobulges, indicating coordinated collapse on scales of thousands of light years. The formation of structure and the ignition of nuclear fusion are closely coupled in time and space, suggesting a high degree of temporal and spatial synchronization. You measure velocity dispersions, metallicity gradients, and cluster ages, all consistent with rapid, organized star formation, rather than the gradual, chaotic growth predicted by hierarchical models. Ultimately, cosmic star formation rates demonstrate that the early universe does not evolve evenly. Time, as measured by the emergence of stellar populations, is punctuated. Some regions experience rapid, almost instantaneous bursts of activity, while others lag behind, creating a heterogeneous, temporal landscape. Observation shows that these bursts are not anomalies, but intrinsic features of early galaxy evolution, encoded in light, chemical composition, and structure. The universe, as measured, unfolds in a sequence of compressed intervals rather than a uniform flow. You are confronted with a subtle but persistent unease. Star formation is both measurable and accelerated, chemically enriched and synchronized, challenging assumptions about the pace of cosmic evolution. Light reveals a cosmos that ages unevenly, punctuating epochs with intense activity, while leaving other regions comparatively quiescent. Measurement confirms that temporal compression is real, forcing the recognition that the universe's early history is far more abrupt, coordinated, and paradoxical than intuition or standard models suggest. The first light problem. Cosmic dawn. The moment the first stars ignite should be gradual. JWST shows pockets of light that appear fully formed, signaling an uneven ignition, contradicting your expectation of smooth chronological progression. In the standard picture, the first stars, population 3, emerge from pristine hydrogen and helium clouds, slowly coalescing under gravity. Formation begins in small, isolated regions, with ignition spreading progressively across the universe. Yet, when you observe the earliest galaxies, light appears already intense and structured, as if stellar populations had been established in concentrated bursts rather than a steady emergence. Measurement confirms that these regions are neither dim nor diffuse. They are luminous, massive, and chemically evolved. Spectroscopy reveals that these early luminous pockets contain metals, indicating previous generations of stars have already lived and died. The paradox is clear. Nuclear fusion in stars requires time, even in massive, short-lived objects. Multiple stellar generations are necessary to produce the observed chemical enrichment. Yet the light from these galaxies arrives at your instruments corresponding to epochs only a few 100 million years after the Big Bang. Observation imposes a direct constraint. The first light in these regions is too bright, too structured, and chemically mature for the available time. The spatial distribution of this early light compounds the problem. Bright galaxies are found in both dense filaments and isolated voids, suggesting that early ignition was neither locally confined nor uniformly delayed. Measurements of stellar density, emission intensity, and spatial morphology indicate coordinated formation on scales of thousands of light years. Structures are coherent, disks and bulges already forming, while adjacent regions may remain nearly dark. Observation shows a universe that ignites unevenly, with localized bursts of maturity juxtaposed against areas of relative quiescence, defying expectations of gradual, uniform cosmic dawn. Even the energetics of early light challenge assumptions. Photons from these galaxies show high ultraviolet luminosity, implying large populations of massive stars burning rapidly and efficiently. Feedback from supernovae, expected to regulate and suppress further star formation in such compact regions, does not appear to have disrupted this early illumination. Measurement demonstrates that stellar activity is not only accelerated, but resilient, capable of sustaining intense light output without halting subsequent formation. The universe, in these first luminous regions, achieves maturity faster and more robustly than standard models predict. Gravitational lensing reinforces the paradox. Some of the earliest luminous regions are magnified by intervening mass, revealing detail that would otherwise remain invisible. Lensed images confirm structural complexity and concentrated brightness, indicating that even the most distant, observable pockets of light are organized and chemically evolved. These measurements show that the universe's first light is not a slow, diffuse glow, but a mosaic of mature, rapidly formed stellar systems, each following a local tempo distinct from the average cosmic timeline. Ultimately, the first light problem forces a reconsideration of the pace of cosmic evolution. Observation reveals that the ignition of the earliest stars is uneven, compressed, and locally accelerated. Time, as measured by the emergence of luminosity and chemical processing, is not smooth, but punctuated. Light from these regions carries the record of processes that exceed the expected temporal allowances, encoding histories that seem premature relative to standard cosmological models. You are left with a quiet, persistent unease. The universe does not awaken gradually. Its first light, as measured by JWST, is sudden, mature, and spatially heterogeneous. Observation alone dictates the paradox. Cosmic dawn is both real and uneven, revealing a universe that defies expectations of smooth temporal progression, while remaining fully consistent with measurement. Time, at the very moment of first illumination, is not uniform, and the early cosmos already hints at complexity, coordination, and acceleration that you cannot reconcile with intuition. Interstellar dust in the early universe. Dust, the product of dying stars, exists in surprising quantities. Its presence in galaxies at extreme redshift indicates prior cycles of star formation, further compressing the temporal story of cosmic evolution into impossibly brief windows. In conventional understanding, interstellar dust forms primarily in the atmospheres of asymptotic giant branch stars and in supernova ejecta. These processes require stellar evolution spanning tens to hundreds of millions of years. Yet light from early galaxies shows significant dust content at epochs when the universe itself is barely a few 100 million years old. Measurement confirms that the cycles of stellar birth, evolution, and death necessary to produce this material have occurred far faster than standard models would allow. Spectroscopic signatures reveal that this dust is chemically rich, containing elements such as carbon, silicon, and oxygen. Its distribution within galaxies is non-uniform but coherent, often concentrated in regions of ongoing star formation. Light absorbed and re-emitted by dust clouds allows you to infer the presence of substantial amounts of obscuring material, suggesting that early stellar populations have not only formed, but have already processed and expelled material into the interstellar medium. The implications are stark. Multiple generations of stars must have lived and died in intervals that are, by conventional calculation, extremely brief. Even isolated galaxies exhibit substantial dust content. You might expect that environmental isolation would slow enrichment, yet observations show chemical complexity comparable to that of galaxies embedded in dense filaments. The production and incorporation of dust into subsequent star formation proceed with surprising efficiency, suggesting that temporal evolution is locally accelerated and not strictly governed by proximity to dense cosmic structures. Measurement confirms that the early universe does not evolve uniformly. Some regions achieve maturity, while others lag, revealing a heterogeneous temporal landscape. The presence of dust also affects observational interpretation. It absorbs ultraviolet and visible light from stars, re-radiating it in the infrared. JWST's infrared capabilities reveal these dust-enshrouded galaxies, allowing you to detect both obscured star formation and the dust itself. Analysis shows that dust-to-gas ratios in some high redshift galaxies approach values typical of much later cosmic times. Observation demonstrates that the universe's chemical evolution, as recorded in light, occurs far faster than the naive timeline suggested by the expansion of space alone. Furthermore, dust plays a functional role in subsequent star formation. It promotes cooling in molecular clouds, allowing gas to collapse more efficiently into new stars. Its early presence implies a feedback mechanism in which the universe accelerates its own evolution. Stars produce dust. Dust facilitates more rapid star formation, and new stars continue the cycle. Measurement of emission lines, continuum radiation, and dust absorption profiles shows that these processes are operating in concert at epochs when, according to standard timescales, only the first generation of stars should exist. Observation encodes a temporal compression that cannot be reconciled with naive chronological assumptions. Ultimately, interstellar dust in the early universe highlights the paradox of compressed cosmic time. Light confirms that multiple stellar generations have already contributed to chemical enrichment and star formation. Dust is not merely a tracer of prior activity. It is evidence that time, as measured by the progression of chemical and structural complexity, is uneven and accelerated in certain regions. Measurement alone demonstrates that the universe operates on overlapping temporal scales, with some systems maturing far more rapidly than global averages would suggest. You are left with the quiet unease that dust, an artifact of stellar life cycles, serves as a record of accelerated history. Its presence at extreme redshift confirms that evolution in the early universe is punctuated, spatially heterogeneous, and temporally compressed. Observation does not permit speculation. It dictates a paradox. The universe achieves chemical and structural maturity faster than your models predict, encoding in light and dust a chronology that defies simple, linear understanding. Measuring cosmic entropy. Entropy is a measure of disorder and time's arrow. Yet the ordered structures observed in early galaxies suggest pockets of low entropy, where high entropy should dominate, revealing a universe that does not conform to your intuitive thermodynamic narrative. In conventional terms, the universe begins in a state of low entropy at the Big Bang and gradually increases in disorder as matter spreads, structures collapse, and energy disperses. Yet when you observe galaxies forming only a few 100 million years after the initial expansion, you find coherence, organization, and structure that implies local reductions in entropy, contrary to the smooth progression expected from large-scale thermodynamics. JWST observations show galaxies with well-formed disks, bulges, and rotational coherence existing alongside chemically enriched interstellar media. Their stars are clustered, feedback processes have not disrupted formation, and dust and metals are distributed in an ordered manner. Measurement confirms that these structures are organized on scales that require coordination of mass, energy, and angular momentum, producing low entropy regions embedded in a universe that, on average, is still in its early stages of evolution. The paradox is that, at these early times, entropy should dominate on both local and cosmic scales. Yet observation records pockets of remarkable order. This paradox is reinforced when you consider stellar populations. Massive stars form rapidly, die, and produce metals and dust. Yet the process does not appear to randomize the local environment sufficiently to erase order. Instead, new generations of stars emerge in patterns and distributions that maintain coherence. Light and spectral measurements encode evidence of organized feedback loops, where energy and matter are recycled in a manner that preserves structural stability rather than increasing chaos. Observation shows that the early universe is not a simple, homogeneous increase in disorder. It contains regions where the arrow of time, as inferred from thermodynamic progression, is locally modulated. Even the gravitational scaffolding implied by dark matter halos contributes to the anomaly. Dense regions collapse efficiently, producing organized filaments and clusters that guide baryonic matter into ordered structures. Lensing measurements reveal that dark matter halos are coherent and sufficiently concentrated to accelerate structure formation, effectively creating low-entropy islands within a broader, higher entropy background. These islands do not violate physics. They manifest natural consequences of gravitational dynamics, yet the speed and scale at which order emerges remains striking. Measurement demonstrates that entropy, while statistically increasing on a universal scale, can remain locally constrained in ways that your intuition does not anticipate. Chemical enrichment adds another layer of complexity. The presence of metals and dust indicates previous stellar processing, which should contribute to energetic dispersal and increase disorder. Yet the very same galaxies hosting these elements maintain rotational symmetry, disk integrity, and star cluster organization. Observation indicates that high-energy processes, which ordinarily drive entropy upward, coexist with local order, suggesting that temporal progression and thermodynamic evolution are not strictly aligned. Measurement records a universe capable of sustaining pockets of low entropy, even in epochs of rapid growth and transformation. Ultimately, measuring cosmic entropy reveals a subtle tension between observation and expectation. The universe is simultaneously evolving, accelerating, and structurally coherent. Light, chemical signatures, and gravitational mapping all point to regions of low entropy that appear prematurely and persist despite high-energy feedback and rapid formation. Observation alone dictates that entropy is not uniform. The early universe contains spatial and temporal heterogeneity in disorder, with low-entropy systems embedded in a larger, increasing entropy background. You are left with a quiet, persistent unease. Entropy, the measure of disorder, and the arrow of time, does not progress uniformly across the cosmos. Light from the earliest galaxies shows order emerging where disorder should dominate, revealing a universe that is at once coherent and chaotic, accelerating yet locally constrained, predictable yet unexpectedly organized. Measurement exposes the paradox. Cosmic entropy is heterogeneous, encoding a subtle and profound discrepancy between your thermodynamic expectations and the reality recorded in the earliest light. The illusion of sequential causality. The sequence of formation implied by JWST observations does not align with classical causality. Stars, galaxies, and black holes appear in orders that cannot be strictly linear, forcing a reconsideration of how temporal sequences emerge from observation. In standard cosmology, structure formation follows a predictable hierarchy. Small fluctuations in density collapse into stars. Stars assemble into galaxies. Galaxies merge and grow. And black holes form at centers as a consequence of these processes. Yet the light you now measure reveals systems in which these events appear decoupled or accelerated, as if different components evolve independently, compressing or even inverting expected sequences. Galaxies at extreme redshift contain fully formed stellar populations alongside central black holes that rival their host in mass. Stellar disks are already organized, star clusters chemically enriched, and dust has been produced, even though the time available since the Big Bang is minimal. Measurement confirms that black hole growth and stellar evolution occur almost simultaneously, rather than one following the other in predictable succession. Observation alone reveals a paradox. The universe appears to develop multiple, interdependent structures at overlapping temporal intervals rather than in a strict, linear chain. The paradox extends to the distribution of chemical enrichment. Metals, dust, and molecular gas appear as galaxies in amounts that imply multiple cycles of star formation. Yet these cycles overlap with the growth of massive black holes and the assembly of galactic disks. In some cases, chemical signatures suggest that supernova feedback has already influenced subsequent generations of stars, even while black holes continue to accrete rapidly. Each measurement encodes a history in which cause and effect are entangled across scales, obscuring a simple chronological narrative. Even isolated galaxies illustrate this non-sequential behavior. Systems in sparse cosmic voids show mature stellar populations, organized structures, and dust enrichment alongside compact black holes, despite lacking external mergers or interactions. The temporal order of collapse, ignition, enrichment, and accretion is inconsistent with conventional models. Observation demonstrates that sequence is a local property rather than a universal one. Different regions of space can evolve at different paces, and the order of events is not strictly imposed by global causality, but emerges from local dynamics and interactions. Gravitational lensing adds further complexity. Light from distant galaxies follows multiple curved paths, introducing measurable time delays that can be used to probe sequence. Yet, even accounting for these delays, the inferred progression of structure does not fit a single chronological framework. Stars may appear to form before galactic disks are fully in place. Black holes may grow alongside their host galaxies rather than after them. And chemical enrichment occurs in overlapping bursts. Measurement records a universe in which causality is locally consistent, but globally heterogeneous, producing apparent inversions or accelerations in sequence. The cumulative implication is unsettling. Classical intuition assumes that temporal order emerges naturally from sequential causation, that structure follows a logical progression from simple to complex. Observation contradicts this assumption. Light encodes histories in which multiple processes operate in concert, overlapping in time, and sometimes appearing to preempt one another. The sequence you infer from redshift and morphology is not universal. It is a patchwork constructed from local clocks, overlapping tempos, and emergent interactions. You are left with a quiet disquiet. The universe, as measured, is temporally layered, locally consistent, yet globally ambiguous. Stars, galaxies, and black holes do not always follow the order you expect. Observation, precise and repeatable, exposes a cosmos in which sequential causality is an emergent property rather than an absolute law. Time, evolution, and structure are intertwined in ways that challenge intuition, revealing that the history recorded in light is neither linear nor uniform, but patchwork, overlapping, and quietly paradoxical. Spatial expansion versus temporal compression. Space expands uniformly on large scales, but early universe structures suggest that temporal processes compressed into shorter intervals than expected. You measure the universe's expansion through redshift, Hubble's constant and large-scale surveys, confirming that space itself stretches evenly, carrying galaxies apart at predictable rates. Yet within this expanding fabric, the evolution of matter, the collapse of gas, the ignition of stars, the formation of galaxies, appears to be decoupled from spatial expansion. Light from early galaxies indicates that processes normally thought to require extended intervals occurred rapidly, independent of the background rate at which the universe itself is growing. Consider the first galaxies revealed by JWST. Their stars are chemically enriched. Dust is abundant, and supermassive black holes already dominate cores. Measurements of these systems suggest that entire cycles of star formation, enrichment, and structural organization occurred within a few 100 million years after the Big Bang. Meanwhile, space between these systems continues to expand at a steady, uniform rate, carrying galaxies apart, but not slowing or accelerating the processes within them. Observation demonstrates a dissonance. While the metric of space expands linearly on large scales, the metric of evolution compresses locally, producing mature systems in intervals far shorter than standard models would allow. The paradox is reinforced when comparing galaxies at similar redshifts. Some evolve more rapidly, forming disks, bulges, and dense stellar populations, while others remain diffuse and primitive. This heterogeneity occurs within regions of space that, on average, share the same expansion history. Measurement confirms that spatial expansion does not dictate temporal evolution. Local processes unfold according to conditions, mass distributions, and feedback loops, rather than the universal pace of cosmic stretching. Temporal compression becomes a local property superimposed upon global uniformity, visible in spectra, morphology, and chemical composition. Gravitational dynamics further illustrate this decoupling. Dense, dark matter halos accelerate the collapse of baryonic matter, producing ordered galaxies earlier than expected. Lensing measurements reveal multiple distant systems whose apparent age and structure defy the timeline implied by the expansion of space alone. Light traveling along different paths reaches you simultaneously, yet encodes histories of rapid, independent development. Measurement shows that evolution is not strictly tethered to expansion. Galaxies form, stars ignite, and black holes grow at rates largely independent of the cosmic metric. Even large-scale feedback processes do not resolve the paradox. Supernovae and stellar winds inject energy, redistribute matter, and regulate local star formation. Yet these processes operate within compressed intervals, producing fully formed structures without altering the broader uniformity of space. Observation demonstrates that local temporal compression coexists with large-scale expansion. Time, as measured by evolution, and space, as measured by stretching, are decoupled, yet both real, both measurable, and both undeniable. Ultimately, spatial expansion and temporal compression together reveal the subtle complexity of the early universe. You are confronted with a cosmos in which distances stretch predictably, yet processes unfold at varying and accelerated tempos. Light, spectra, and structure all encode histories that are locally compressed, chemically enriched, and dynamically mature, even while the universe's fabric continues its uniform growth. Measurement exposes a dissonance. Space and time, expansion and evolution, are not tightly coupled. Each proceeds according to its own rules, creating an early universe both coherent and paradoxical. You are left with the quiet, persistent unease that the universe does not age evenly. Expansion is regular, measurable, and consistent, while evolution is compressed, accelerated, and heterogeneous. Observation dictates that temporal and spatial metrics, though intertwined in the same cosmos, are not equivalent, and that standard cosmology cannot fully reconcile uniform stretching with the rapid emergence of structure. The universe, as revealed by JWST, is orderly yet temporally fractured, expanding evenly while evolving irregularly, and quietly defying the linear intuition you bring to space and time. The limits of simulation. Computer models predict galaxy formation with broad consistency. JWST observations exceed these simulations in complexity and timing, showing that even mathematically precise models cannot capture the pace of reality. Simulations begin with initial density fluctuations, dark matter scaffolding, and simple physical laws, evolving these parameters under gravity, hydrodynamics, and thermodynamics. They produce galaxies, star clusters, and black holes that, in principle, reflect the statistical properties of the early universe. Yet when you compare these predictions to what JWST observes, discrepancies emerge not in subtle deviations, but in the fundamental speed and coherence of formation. Simulations forecast that the first galaxies should be small, diffuse, and chaotic. Stars should form gradually. Chemical enrichment should progress slowly. And black holes should remain relatively modest. Observation reveals something different. Galaxies are organized, massive, chemically mature, and often host supermassive black holes. Entire cycles of formation, feedback, and enrichment occur in compressed intervals that simulations, calibrated with standard physics, struggle to reproduce. Measurement confirms that the universe evolves faster and more efficiently than models anticipate. The limitations of simulation are not merely computational. Even with immense processing power and finely tuned parameters, models rely on approximations. Gas cooling, feedback, turbulence, and star formation thresholds must be parametrized rather than derived exactly. JWST observations indicate that the actual universe exploits processes, interactions, and emergent behaviors that are either incompletely understood or entirely absent from these models. Galaxies exhibit structural coherence, chemical sophistication, and dynamic behavior that exceeds any predicted output, revealing that reality is richer and more coordinated than the mathematics anticipates. Furthermore, simulations impose a linear or hierarchical temporal logic. Small structures form first, merge into larger systems, and gradually assemble complexity. JWST shows that this hierarchy is sometimes inverted. Massive galaxies with fully formed disks and enriched stars appear at epochs when models predict only primitive fragments. Feedback, starburst events, and black hole growth appear compressed and synchronized in ways simulations cannot replicate. Observation exposes a discrepancy not only in detail, but in the fundamental pacing of cosmic history. Even large-scale patterns defy simulation. Filamentary structures, void galaxies, and horizon-scale correlations exhibit coherence and maturity beyond what current models produce. Measurements show alignment, distribution, and organization that imply accelerated evolution and local heterogeneity in temporal progression. Light from these systems encodes histories that exceed the statistical variation built into simulations, revealing that emergent processes operate at scales and speeds unaccounted for by even the most advanced computational frameworks. Ultimately, the universe imposes a subtle, persistent reminder of the limitations of human abstraction. Measurement demonstrates that mathematical precision and physical principles, while powerful, cannot fully reproduce the emergent behavior of reality. Light, spectra, and structure encode a complexity and efficiency that exceed expectation. Observation exposes a cosmos that evolves on overlapping temporal scales, compressed locally, and coordinated across regions that models struggle to capture. The universe is precise yet unpredictable, ordered yet accelerating beyond theoretical anticipation. You are left with a quiet, enduring unease. Simulation provides insight, but it is inherently incomplete. JWST confirms that the universe unfolds in a manner that is measurable, consistent, and yet fundamentally richer than your theoretical constructs. Observation alone dictates the paradox. Even rigorous models cannot match the pace, coherence, and acceleration of reality. The limits of simulation are the limits of expectation, and the cosmos, as revealed in light, continues to surpass the most precise human predictions, quietly asserting its independence from your mathematical intuition, observing what should not exist. Every new early galaxy cataloged acts as a counterexample to standard timelines. Their existence is not speculative. They are measured, repeated, and real. Observation forces acknowledgement that the universe is less constrained by your chronological expectations than believed. JWST captures light from galaxies that should not yet exist according to classical formation models. Massive systems with well-formed structures, chemically enriched stars, and central black holes, all appearing within the first few 100 million years after the Big Bang. Each detection is a confirmation, not an anomaly, that cosmic evolution can operate on a compressed schedule, producing maturity where models anticipate infancy. Spectroscopy, photometry, and imaging converge to reinforce this reality. The chemical compositions indicate multiple generations of stellar processing, while structural measurements reveal disks, bulges, and rotational coherence. Black holes of extraordinary mass reside in galactic centers, demanding growth rates far beyond what conventional accretion physics allows. Every measurement repeats the same paradox. The universe exhibits structures and behaviors that exceed temporal allowances established by standard cosmology. Observation confirms that these galaxies are not the result of error or bias. They are directly encoded in the light reaching your instruments. The paradox deepens when considering statistical abundance. JWST surveys reveal dozens of these unexpectedly mature galaxies across different fields, implying that rapid formation is not isolated, but pervasive. Measurement of luminosity, mass, and metallicity consistently demonstrates that early galaxies defy linear hierarchical assembly. Structures that should be simple and chaotic are instead coherent and evolved. Observation indicates that the universe possesses a capacity for accelerated evolution, independent of the large-scale expansion that governs cosmic distances. Chronology is local, variable, and sometimes compressed beyond conventional expectation. Even the isolated systems pose a challenge. Void galaxies, far from dense filaments or massive clusters, show comparable maturity. Their presence demonstrates that external gravitational scaffolding is not a prerequisite for rapid evolution. Measurements of star formation, rates, chemical enrichment, and stellar population age indicate that these galaxies progress along timelines independent of environmental constraints. Observation confirms that the early universe contains regions where time, as measured by development and structure, proceeds faster than models predict. The implication is clear. Existence itself cannot be fully explained by classical assumptions about sequential formation or environmental dependence. Gravitational lensing amplifies the paradox. Light bent around massive foreground structures reveals galaxies that are both more distant and more evolved than direct observation would allow. Lensed images expose early maturity in systems whose light has traveled over 13 billion years. The delay and magnification inherent in lensing reveal histories that are accelerated, coherent, and surprising. Measurement encodes both spatial and temporal compression, highlighting the contrast between expected timelines and observed reality. Each observation reinforces the conclusion that chronological intuition fails when confronted with empirical evidence. Ultimately, observing what should not exist forces a confrontation with the universe on its own terms. Light, redshift, and structure are consistent, repeatable, and measurable. Each early galaxy catalogs a reality that does not conform to expectation, a cosmos in which time is locally accelerated, evolution is punctuated, and structural maturity emerges faster than conventional models allow. Observation dictates the paradox. Reality itself outpaces theory, compressing development into intervals that challenge intuition, while remaining fully consistent with measurement. You are left with a quiet, persistent unease. The universe, as measured, is less constrained by chronological expectation than your models suggest. Galaxies exist that should not, yet they do. Observation, precise and repeatable, confirms their reality. Each photon carries the record of accelerated evolution, encoding histories that defy linear timelines, revealing a cosmos in which temporal compression is as real as spatial expansion, and where the early universe is more complex, mature, and paradoxical than any calculation could predict. Time as a derived phenomenon. If measurements show mature structures where none should exist, perhaps time itself is emergent, not fundamental. Your familiar temporal markers, seconds, years, billions of years, may describe perception rather than an absolute cosmic substrate. Observations from JWST reveal galaxies, stars, and black holes whose formation histories appear compressed relative to the cosmic clock you assume. The light they emit encodes epochs that, under conventional chronology, are insufficient for the processes observed. Measurement implies that temporal intervals are not universal, but contextual, shaped by local physics, density, and interaction, rather than a single global metric. Consider the formation of massive galaxies at high redshift. Stellar populations indicate multiple generations. Chemical enrichment shows repeated supernova cycles, and central black holes have grown to extreme mass, all occurring when the universe is only a few 100 million years old. If time were uniform and absolute, these processes could not have completed. Observation leaves only two possibilities. Either physical laws are violated, or your conception of time as a linear, global parameter is incomplete. Measurement favors the latter. Time may emerge as a derived property of evolving systems, encoded in structure, motion, and interaction, rather than flowing independently. Chemical maturity provides further evidence. Metals, dust, and molecular complexity arise from stellar evolution, which requires intervals set by nuclear physics. In early galaxies, these intervals appear shortened or overlapped. Spectroscopic analysis confirms multiple enrichment cycles within periods too brief for standard nuclear timescales. Observation indicates that the progression of matter, rather than an external temporal metric, governs apparent time. The universe evolves according to internal dynamics, producing the appearance of chronological sequences that may not correspond to a universal temporal flow. Spatially, the argument is reinforced by void galaxies and isolated systems. In regions with minimal external influence, stellar populations mature rapidly, disks form, and black holes grow efficiently. Local gravitational and thermodynamic conditions appear to dictate the rate of evolution. Measurement shows that time, as inferred from development and structure, is regionally variable. Light from these galaxies encodes histories that are compressed relative to other environments, implying that chronological perception is tied to context, not an overarching cosmic clock. Even large-scale correlations challenge linear time, horizon-spanning structures, coherent filamentary networks, and aligned galaxy spins suggest a level of organization that emerges across distances traditionally considered causally disconnected. Observation implies that evolution can occur in a pattern that does not correspond neatly to a sequential timeline. Measurement encodes relationships between systems that are coordinated without a single global temporal framework, revealing that the order of events may be emergent, relational, and encoded in structure rather than flowing independently. Ultimately, considering time as a derived phenomenon reframes all paradoxes. Galaxies mature too quickly. Black holes grow too early. Star formation accelerates beyond expectation. All become consequences of locally emergent temporal scales rather than violations of physics. Observation shows that temporal markers, while meaningful in human experience, describe patterns of evolution rather than an absolute background. Measurement encodes time in structure, light, and interaction, suggesting that what you perceive as seconds, millions, or billions of years is a reflection of local processes, not an immutable cosmic rhythm. You are left with a subtle, persistent unease. The universe may not possess time as a uniform dimension, but instead encodes temporal experience in the evolution of matter itself. Observation dictates that chronological intuition, built from human perception and earth-bound clocks, cannot fully describe cosmic history. Light, structure, and motion record a universe where time emerges locally, unevenly, and variably, forcing recognition that the flow you assume is not a given, but a derived measure of processes you observe. The cosmos, in its earliest epochs, already hints that temporal reality is relational, emergent, and profoundly counterintuitive. The scale of cosmic time revealed. James Webb's data does not merely extend your observational reach. It compresses and expands your understanding of duration, showing that time, as measured by formation, structure, and evolution, is far more variable and paradoxical than assumed. You are confronted with a universe whose history is more complex and less linear than your intuition allows. Galaxies appear mature within intervals that models deem impossibly short. Stellar populations, chemical enrichment, and central black holes evolve rapidly, creating systems that seem temporally advanced relative to their cosmic age. Measurement confirms that the pace of cosmic evolution is not uniform, but punctuated, regionally variable, and context-dependent. Consider the contrast between early galaxies and the surrounding intergalactic medium. Dense systems evolve quickly, forming stars, disks, and supermassive black holes, while nearby voids remain primitive and chemically unenriched. Light from these regions encodes histories that differ in rate and intensity, revealing that time, as inferred from matter's progression, is not globally constant. Observation shows that chronological markers, redshift, look-back time, and inferred cosmic age provide only a framework. They do not dictate the pace at which structures actually mature. The universe operates with local tempos, compressing or expanding evolution in ways that defy linear expectation. Chemical signatures reinforce this interpretation. Metals, dust, and molecular compounds appear in galaxies at extreme redshift, implying multiple generations of stars have already completed their life cycles. Nuclear fusion imposes physical limits on stellar evolution, yet these limits are seemingly circumvented in early systems. Measurement shows that enrichment, star formation, and structural assembly occur simultaneously or in overlapping intervals, compressing what would otherwise be sequential processes. Observation encodes a universe in which time, measured by developmental milestones, is heterogeneous and locally accelerated. Supermassive black holes present an even starker challenge. Their masses, often billions of solar masses, are inconsistent with the growth rates predicted by standard accretion physics if measured against the age of the universe at their redshift. Light from their host galaxies shows stars and dust already in place, indicating a temporally compressed environment in which multiple high-energy processes occur nearly simultaneously. Measurement demonstrates that the formation of both matter and structure can outpace your standard understanding of duration, revealing time as relational rather than absolute. Even large-scale cosmic structures contribute to this paradox. Filaments, voids, and horizon-spanning correlations display maturity and organization inconsistent with a uniform, linear unfolding of time. Observation shows coherence across scales that are causally disconnected, implying that temporal progression is emergent from local dynamics rather than dictated by a global metric. Light from distant systems carries histories that overlap, intersect, and accelerate relative to one another, producing a record of cosmic evolution that is compressed, uneven, and paradoxical. Ultimately, James Webb's observations force a re-evaluation of what cosmic time means. Measurement alone dictates the conclusion. Time is not a simple, uniform dimension stretching evenly from past to future. Instead, it is encoded in the evolution of matter, the formation of structure, and the maturation of galaxies. Chronological markers provide context, but the underlying pace of development varies, accelerates, and punctuates itself across space. Observation reveals a universe that ages unevenly, evolves unpredictably, and encodes histories that resist simple temporal ordering. You are left with quiet unease. The scale of cosmic time is neither absolute nor linear. Light, structure, and chemical evolution record a universe in which durations are locally defined, overlapping, and paradoxically accelerated. Observation alone exposes a cosmos whose history is rich, complex, and inconsistent with the simple progression you assumed. Time, as revealed by formation and evolution, is emergent, heterogeneous, and profoundly counterintuitive, forcing you to reconsider the most basic assumptions about the duration, pacing, and unfolding of the universe.